welcome back. I'm glad that I'm functioning today. Hopefully you're at home, not at like 2 o'clock in the morning, and you're functioning as well. So today we're going to do a lot of functioning together. And the reason I keep on annoyingly saying the word functioning repeatedly is because it functions to set up the function section of this lesson. That being said, it's time for functions, guys! So with functions, it's pretty darn simple. It doesn't matter how you want to say it, whether you're saying, your classic f of x equals or if you're saying the f of x is going to equal, which is, more coding talk. Either way you want to say it, or if you've got another way that works for you, you do that. Just make sure it's official. It's simply saying that when you enter the term x, you enter your x, and you're going to send it through this particular process. Somewhere here in this process, something's going to get done to that x. That x might be getting squared. That x might be getting multiplied by 2. Either way, whatever you're doing to it, it's going to come out on the other side as a second term. That's going to end up being your y term. That's pretty simple. So there's a few terms you need to know when you're working with functions. The first one's domain. Domain's whatever you stick into a function. Think about it this way. You've got your function f of x. F of x is going to equal something. We're going to make it pretty simple. So we're just going to say x squared. Whatever you put into that x, that's what your domain's going to be. In this instance, your domain could be all real numbers. Sometimes you're going to have a specified domain. For example, you might be only putting in positive numbers. What would an example of a situation in which you might only put in positive numbers and no zeros? Wait for it, guys. Logs. We just talked about these. This is a perfect example of a slightly different domain. So if you have the log of x equaling your function, f of x equals log of x, your domain would be all positive real numbers can be put into this function. That's all it is. So now, what's range? Range is what comes out of the function. So once you've gone through your function, that log of x is going to equal your range. A great example of ranges is that for the function x squared, you can put in any real number. Feel free. So we have our f of x equals x squared. You can put in -4, 2, 8, 10, 39, 2 million, whatever you feel like. But no matter what you put in, it's always going to be a positive number or 0. So 0 or a real positive number. Why is that? Because obviously it's a square. If you take -3 squared, you get 9. It goes back to being positive. And that's going to be your range, whatever comes out of your function. When you're graphing a function, keep that in mind. There's something very important. When you're graphing it, you're going to get that wonderful Cartesian plane. Boop, 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 boop. Your domain, which will be your x terms, will be down here with the domain. And over on this side with your y terms will be your range. Just keep that in mind. So for example, if you're plotting this function and you say you're getting a parabola, so it's a quadratic, boom, beautiful. Your domain, all real numbers, because it's going to keep on going up off in this direction here, off in that direction there, so you've got all the real numbers on your domain. But range, you notice you come down in this area down here, there's nothing. So your range is going to be, say, this is at 2. In that case, your range would be all real numbers equal to or greater than 2. That's all you've got to worry about. Last thing when you're talking about functions is the idea of the image. Image sounds a little odd. All it means, what numbers come out of the function. So in other words, what numbers coincide between the domain of the function, which numbers coincide between the range of the function and the range of essentially all numbers. So your image of your function are going to be your pairs that are going to be your coordinate pairs. So for example, for the function back to x squared, your image would include 1, 1, 2, 4, on and on, 3, 9, 4, 16, good old numbers. And all that means is those are going to be points on your parabola. At any point on your parabola or on your function is going to be part of the function's image. Pretty simple. So now, when you're looking at functions, there's something that's very important with the functions when you're looking at functions on a graph. And that's the idea of odd versus even functions. You might say odd and even functions. Seems odd, right? All it means is it's talking about the directionality of the ends of the function. This is mostly talking about curves, mind you. For example, a linear function, if we're just talking about a line that's going up on your plane, this is going to be an odd function. But it doesn't work quite as well when you have this, because you need a turning point to truly understand what I'm talking about. Here you see this end ends going up, this end ends going down. So they're not the same, because obviously odd is kind of the term for different, whereas even means the same. Now, when you're looking at a parabola, like that, you see both of the ends finish heading upwards. Or, if you have a negative parabola, like that, they both end going down. Either way, it's going to be even because they're both going to be the same. However, what if we up our power 1? We saw what happened when you have a linear function, x to the 1. We saw what happened when you have a parabola, x to the 2. Now what if you have x to the 3? Whoop! Oh no! So this end is heading down, this end's heading up. Now you have an odd function because one end's heading down, one end's heading up. Pretty straightforward. So all it comes down to is that an odd function is a function that comes to the point where it's either the bottom comes in heading up and leaves heading, if the bottom leaves the graph heading down, so for example with the idea of a cubic, or we could do even more complicated version of the cubic, you've got them heading in different directions versus with say a x to the 4th graph where you have both ends heading off in the same direction, that nice W shape. Even, they're heading in the same direction. Odd, because they're heading in different directions. Mind you, some functions have no direction, have no even or odd, because they continue on flipping back and forth infinitely. For example, a great example of this would be a sine curve. With the sine curve, you notice you start off at your 0, and it's just going to go up and down, on and on and on. So it's not going to have an even or an odd, because at any point you might choose, it's still going to be going even, odd, even, odd. That about covers it for the idea of even and odd functions. So now that you know that, you can use that to help identify what functions you're talking about. For example, a cubic function will always be odd. So if you're trying to identify what power your function's to, and you see a function doing this, you're immediately going to know, okay, it's not a cubic function because one end is heading up and the other end's heading up too, instead of one heading up and one heading down. Boom, there we go. Now, there's another type of equation that you can work on with functions. That's the idea of composite functions. What happens if I take a function and stick it inside another function? For example, take the function fx. We're going to go back to our favorite function because it's a pretty function and it works well. We're going to go back to x squared. F of x equals x squared. Now, we're going to look at a second function, g of x. G of x is going to equal 2x. What happens if we created the function f of g? F of g, which can be described like this, with that nice little circle in between, or just with the classical function notation, f of g of x, is simply going to be, you compute g of x, and then you insert the result of that into f of x. So, running through this, we know f of x is x squared, g of x is 2x, so you take the term 3. So first you put it through g of x. So up here we have our x squared, and then 2x. So we'll start down here. 2 times 3, you get a 6. And then you ship it upstairs to the next function. 6 into the x squared, 6 squared, will then equal 36. Just that simple. Now what if we wanted to properly combine them so that you can have a single function that equals the f of g? All you have to do is put them together, keeping the x. So your g function is going to be inserted into where the x was in the f of x. So where previously you had x squared, you're going to insert that 2x. And now what you're going to have is going to be 2x squared. Now you have the 2x squared, you can go and say, okay, I can get this down a little bit, and all you get is a clean 4x squared is going to equal f of g. Boom. Now, what about another type of function, the classic identity function? An identity function is the simplest function possible. All it does is it returns the same number entered into it. So any number in the domain has the equivalent number in the range that's going to come out. All this means is that f of x, the function, is going to equal x. The number you put in, the x, will then equal itself. Pretty straightforward. And this one is going to have a graph on the Cartesian plane of simply a linear line with no intercept. So it's going to have an intercept of 0. Boom. That's all it is. That is the identity function. Now, there's another idea when it comes to functions, which is the idea of one-to-one and many-to-one functions. Many-to-one functions are when you have your domain and many x terms will result in the same y term. The perfect many-to-one function is a constant function. The f of x equals any number. So say n, or in this case we'll say 3. So if f of x equals 3, any number, many numbers that you put into here, many numbers because there's a lot of them, any real number inserted into here will end up with the result being 3, and that's a single result. However, a one-to-one function would be an example of that, would be the identity function, which we just showed you. No matter what happens, any real number that you insert into the function will have will have the same real number come out, but no two numbers, no two x's that you can insert into this function will result in the same y. Another more common example that you might see of many to one functions would be the parabola. If you insert in the x term of -1 and you insert in the x term of 1, they will still both result in the same y term. So keep that in mind if you're assuming that your focal point is going to be at 0. So in that case, you're going to have the same y. So many terms from x will then equal the same term from y. That's all there really is to that. It's the idea that any function we defined by if multiple x terms can equal the same y term. So in other words, and there's an easy test to do this, it's the parallel line test. So all you do is you look at your function and you say you've got it drawn on your Cartesian plane, and you say, is there any point in this function where I can draw a parallel line to the x-axis through my graph and have it intercept 2 points on the function? For example, with the quadratic function here, yes, there is a point. There's many points in fact. So it's a many-to-one function. Versus with a linear graph, at any point you draw a line through it that's parallel to the x-axis, it's only going to intercept a single point on the graph. Now, you might be thinking, okay, so there's many-to-one and there's one-to-one functions. Can there be a one-to-many function? For example, you'd be like, how about a circle function? Haha. Because, you see, a circle function isn't a real function. It's an imposter function, in fact. Because it doesn't actually exist. The definition of a function is that for every x term, there must be a unique y term. A circle function doesn't have that. For every x term, say for the x term of 2, if you have an x term of 2, then you won't have a unique y term because you'll have this term here and this term. So you're not sure what your output's going to be. Keep that in mind because that's the other test you could do for a function. Whereas you could use the horizontal line to test if a function is many to one or one to one, the vertical line test is a wonderful test to decide, is a function an actual function? If you could draw anywhere on the function a vertical line that would intersect 2 points on the function, then that is not an actual function. Finally, we have to talk about inverse functions. Inverse functions are pretty straightforward. The idea is that you take the function and what you would have originally made your domain, you then make your range. So your f of x and your, say your x squared, get flipped. So once you do this, the easiest way to do it is to set f of x equal to x and your x equal to f of x. So you do this, and what you'll get is x equals f of x squared. You solve for that, you'll get the square root of x equals f of x. So here's the question though. What happens if you square root a number? Remember, you always have this plus or minus sign in front of it. But remember what we just talked about though. You can't have plus or minus with a function because with a function it's very important that the x's, whatever you input into the function, whatever you input into this f of x, has a single result that comes out. So you can't have a positive or negative result. This means that this function would then be invalid. So you have to keep it as the square root of x. And that would have a domain of strictly positive numbers. Now, there is a way around this though. What you do is that you divide that up into two functions. The positive function stays here, and then to give you the full picture, what you would do is you would add in the negative function. The negative square root of x would then also equal a new function, say g of x, and f of x and g of x on the graph would then draw the picture of the inverse function. And that's all about all you need of inverse functions. Also remember, there is such thing as a self-inverse function, and it's the same as an identity function. A self-inverse function is simply an inverse function where the function itself is the same as the inverse of said function. For example, for the function of f of x equals x, well, you can flip that around and it's going to be the exact same thing. F of x will equal x. If you insert f of x where x went and x where f of x went, it's the same thing. And that covers it for functions. So everyone, go have a good break and enjoy your continued mental function.